Hello, my name's Daryl Korn, and this is my walkthrough of Homework 5. So let's get into it. We'll start with the code here. This is for training my support vector machine. So bring in the pandas packages, or the Python packages, bring in data. Here I set if I want to scale my data or not. And then here I'm using sklearn's grid search cross-validation transformer to find different parameters for my function, for my classifier. I find that it's a bit more efficient than using the typical k-fold function because you can split the jobs across your CPU cores and parallelize it. So it's the same end product, of course. You can see here we have different splits here, 4 different splits and their scores as well as their training there. And then I convert all of this into a pandas data frame, which allows me to graph it very efficiently. So here is a subset of my support vector classifier tests. My MLP tests are very similar. We select the scaling or not. We use grid search to find the best parameters, and graphing it looks a bit like that. That one's a bit messy. My apologies. Okay, and this one I can show the outputs. These all take a very long time to run, so I'm not going to do it within the video. But here we use the best parameters that we found to train our classifiers on the full set of test data using cross-validation. So here I'm outputting the general performance metrics. Here I output the confusion matrices for each of the classifiers. And then here I'm looking at the precision recall curves for each individual class and comparing the two classifiers. ROC curves for the two classifiers per class. And lastly, we look at the mislabeled, or not mislabeled, but like samples with certain confidence levels, I would say. Okay, now let's look at the results then. So starting with the support vector classifier. For this, I attempted 2 different kernels, the radial basis function, RBF, and polynomial, as well as 2 different scalar techniques, standard and no scaling, and standard scales everything to be between -1 and 1. And I found, interestingly, that the best parameters for this function were with the RBF kernel and no scaling techniques, which is surprising because that's usually pretty common for, it's pretty common to use scaling for support vector classifiers. And so my theory is that the data is essentially already scaled because each of the values represent a pixel intensity between 0 and 255. So each field really is already on the same scale. So I guess using that scaling function just didn't really help it at all. And of course, my best C value that I found was at 5. Okay, on to the multi-layer perceptron classifier. For this, I attempted 4 different combinations of layers and nodes. So 10 layers, 10 nodes, 100 layers with 10 nodes, 10 layers with 100 nodes, and then 100 layers with 100 nodes. And of course, 2 different scaling techniques. And my best function that I found, or the best parameters that I found, were with a standard scalar this time, and where the layers had 100 layers, or we had 100 layers with 100 nodes each, and an alpha of 0.1. This did give a training accuracy of 100%, so it's overfitting a little bit. So we'll bump up the alpha for remaining tests, and this gave a test accuracy of about 89.5%. So we can see here that the We don't have a whole lot of underfitting and not a whole lot changes with the alphas for the standard scaler. For the unscaled data, well, the values are a little bit all over the place. So scaling definitely helps here. Um, but we certainly see that once we are increasing alpha to around 10, we're really starting to overfit our model, and the testing accuracy is really starting to drop off, similar with the unscaled data in figure 3.2. Okay, to compare our fully trained models, this is with, we're not using cross-validated anymore. We are testing on the unseen test data. It seems that the SVC has a slightly better ability to generalize because it has slightly better precision recall, F1 score, and accuracy, just a little bit. The area under the score metrics for both classifiers are the same, so no real difference there. And this, for future reference, area under the curve for the precision recall curve, and then area under the curve for the ROC curve. All right, let's compare the confusion matrices so we can see how each classifier is doing on the individual classes. So overall, the classifiers are fairly similar, especially on the trousers class. We can see here um, the MLP correctly guessed about 963 trousers, whereas the SPC correctly guessed 960. So very similar there. They both did very well in that class. Some classes where they started to mess up a bit more was between the pullover and the coat classes. These do look fairly similar, and the classifiers kind of got one strength was the other's struggle. So the MLP classifier, it mislabeled a lot of coat data. It looks like it was actually pullovers samples, whereas this, the SVC, actually mislabeled more coats as pullovers. So, yeah, they kind of traded off there for that class. Okay, onto the precision recall curve. Again, both classifiers had an area under the curve of 0.94, so it's not a huge difference between them here. But some small differences are that the MLP had this strange drop off for the pullover class. So MLP is the blue line, and the orange line is for the SVC. And so this caused the SVC classifier to have a much higher area to the curve for pullover specifically. You can see it here in figure 6.6. But the MLP did slightly outperform the SVC on other classes such as t-shirt, coat, and dress. And like we can see here in the dress class in figure 6.5, the blue line just kind of butts out just a bit further than the orange line, showing that it's going to be slightly more optimal to choose the MLP classifier for certain thresholds. Okay, onto the ROC curve now. Again, the both classifiers had a similar area under the curve score of 0.98. So both classifiers already have a pretty good trade-off between false and true positives, but some small differences are that the MLP was a bit better at dresses, where the SVC was a bit better on the pullovers. We can see that this orange line is just butting out ever so slightly from the MLP blue curve. Next up, we'll compare the different predicted probabilities between the classifiers. So using sklearn's predict probabilities function, we're going to return a confidence score for each sample, and that score is going to be between 0 and 1. And 0 or 1 represent a very confident score, or a class of, yes, a very confident prediction that the sample is in one class or the other. If this score is around 0.5, then the classifier is not sure which category to really put it into. So here in figure 8.1, I've circled where these different confidences kind of fall on this graph, I have circled in green where both classifiers are very confident at the sample that they just predicted, because MLP and the SVC, they both are at 1 or they're both at 0. So they're pretty confident about sorting that sample. The yellow circles show where the SVC was confident because it's at 1 or 0, but the MLP was unsure. It's at its 0.5 mark. The red is kind of the inverse of that, where the MLP is confident at 0 or 1, but the SVC was not so confident as to where to put that sample. And lastly, the black circle is showing where both classifiers were unsure of where to classify the sample. That's going to fall dead center of the graph. And a pattern you kind of see when you create these graphs are that the more dense graphs show where the classifiers they have less confidence overall about these classes, and a more sparse graph like here in figure 8.2 for trousers, we saw from earlier that both classifiers were pretty strong on the trousers class. So that results in a fairly sparse graph here. Whereas, pullovers, which we saw, they were not confident on a lot of them, and that creates dots just about everywhere. All right, I realize we're nearing the end of our time, so we'll quickly just look at some of the samples that at different confidences. So some samples where both were very confident are over here. We can see just by looking at them that it's fairly easy to sort these samples. Like that's clearly a t-shirt. These are clearly pants. Whereas both are unconfident, these are some tricky samples. This one is apparently a dress, but I would agree that it does look a lot like a coat. And this just kind of looks like a blob. That one's hard to tell what it is, but it is a coat apparently. And down in the corner here, I have where both classifiers, one was confident, one was not so confident. And these kind of follow some middle line where it is kind of hard to tell what they are, but not as difficult as where they are both with low confidence. So I think that's a strange picture for trousers. I'll give him that. Okay, so to wrap up homework 5, I believe that the SVC classifier shows the best ability to generalize for this particular problem. The MLP classifier, it did give similar results, but it just slightly underperformed when you averaged all the metrics together, and it is a bit more complex than the support vector classifier, so it makes sense to just go with the SVC for this solution. And again, to reiterate my results, these are the parameters that I found that worked best, and these were the final performance metrics. All right, that concludes homework 5. Thank you.